Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my BEng Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, so question 9 on the 2020 paper was all your sequences and your patterns and sequences basically, okay? So let's find the page in the log tables that's that. Sorry, I don't know which way I should be going. There. Okay. So I'll come back to that page in a minute, but I just like to have it on sequence and series when I know it's a patterns or sequence and series questions. The following sequence of patterns is used to create matchsticks to form equilateral triangles. Pattern 1, 3 matchsticks, pattern 2, okay, pattern 3, okay. Complete the table below to show the number of matchsticks required to make each of the first 6 patterns of the above sequence. Okay, so I need 3 matches in pattern 1. I need 1, 2, 3, 4, 5, 6, and 7 in this one. Okay, so 1, 2, 3, 4, 5, 6. We go across the bottom 7, 8, 9, and then across the top 10, 11. Okay. Now, at this point, you have 2 options, okay? You can do it visually if that's the way your brain thinks, okay? In that you can add on to your pattern, okay? So there's 1, okay? So I'm going to say he's 1, okay? And then here they added on 2 more. Let's change color. And then they added on 2 more, okay? So in my next one, I'm going to do like this. Okay, and let me count the matches. So 1, if my pen would work for me, it would be lovely. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go across the top. 9, 10, 11, 12, 13, 14, 15. Okay, and you can draw on 2 more triangles and so on and so forth. Okay, so if you're a visual type person, that's exactly how you should do it. Okay, you're probably guessing that I'm not a visual person from the way I'm describing it, and you can see how poorly I draw and so on and so forth. So I'm much more logical, I suppose, and mathsy. So I'm going to look at the pattern between the numbers here to see if there's a pattern, okay? So I'm looking at the difference between 3 and 7 down here, 3, 4, 5, 6, 7, and that's a +4. I then look at how do I go from pattern number 2 to pattern number 3? What's happening, okay? And 7, 8, 9, 10, 11, that's a +4, okay? And 11 to 15, 11, 12, 13, 14, 15, that's a +4. Okay, so without having to subject you to any more of my poor drawing, I know he's going to be a +4. He's a 19, and I know he's going to be a +4, 20, 21, 22, 23. Okay, so I'm not saying one method is better than the other at all. In fact, it's not, okay? But it does depend on how your brain is wired and whether you're a visual. And then you should absolutely draw the patterns, and you can draw them out here if you want, okay? Draw the patterns, count the matchsticks. Or if you're, I suppose, more numbers based, then this method might suit you. Either way, figure out how many matchsticks is in it, okay? And the other thing is, a typical question that gets asked here is to draw the next pattern. So no harm practicing drawing even just one pattern like I drew here just to do it. Okay, B part 1, how many matchsticks are required to make pattern 10 of the sequence? Okay, so no fancy maths here from me at all. I don't see the need for them, so I don't do them when I don't have to. Okay, so 6, 7, 8, 9, and 10. And of course, I'm just going to add on my 4s. So 23 and 4, 23, 24, 25, 26, 27, 4 more, 28, 29, 30, 31, 35, 39. So 39 matches. Okay, see above for workings out. Okay, so that's how I would give my answer if I were sitting in an exam right now. Could you draw this table as part of B? Absolutely, you could. Okay, so again, it just depends on personal preference. Part 2, find a formula for Tn, the number of matchsticks required to make n of the sequence. Okay, so this is a question that some students hate because you have to come up with a formula. I actually like it because I have a structure for it. Okay, so let me explain what am I talking about. Well, again, now I go back to my log tables, and you can see that in these log tables, there's two formulas here already for Tn. Okay, a bit hard to see because the resolution isn't great, but anyway, if I zoom in, it's a little bit better. So a Tn formula here and here. Okay, so what's the difference? Well, the difference is the type of sequence that you're dealing with. So there's two here, an arithmetic sequence, or arithmetic as some pronounces it, or geometric sequence. The difference between these is arithmetic, you're adding or subtracting the same number to get from term to term. So your terms, T1 is the first term, T2 is the second term, T3 is the third term, Tn is the nth term. So it doesn't matter what one you're talking about. You can call it generically Tn, okay? So that's some term, whatever term you want it to be. Okay, they're the terms or the numbers in your sequence. So if you're adding or subtracting the same amount to get from term to term, it's called an arithmetic sequence. And if you have established that it's an arithmetic sequence that you're dealing with, you're looking at the Tn formula here and the Sn formula. In the following, Tn is how you found out what is the nth term, and Sn is the sum of the first n terms. Okay, in both of these formulas, A is the first term and D is what we call the common difference, D being that number that you're adding or subtracting to get from term to term. The other type of sequence that matters to you is a geometric sequence, and that's where you're multiplying or dividing by what's called a common ratio to get from one term to the other. So an example of a geometric sequence would be 4, 2. 2 divided by 2 is 1. 1 divided by 2 is a half divided by 2 is a quarter. Okay, and so on. Or another geometric sequence could be 3, 6, 9, 12. No, that's an arithmetic. Sorry, I'm adding the same amount. It would be 3, and then 3 3s are 9. 9 3s are 27. 27 by 3 is 71, so on and so forth. Okay, so that's an arithmetic, geometric sequence where we're multiplying by 3, and this one, my common ratio would be a half. Okay, so the first job always in a sequence is to figure out which type of sequence are you dealing with, because you can see there's different Tn and Sn formulas for each type of sequence. Okay, so that's why I like this question, I suppose, because I know that those tools are in the log tables for me to work with. So how do we do it now next? Okay, well, let me go back to my sequence. You can see I'm adding 4 to each one. Adding or subtracting makes it an arithmetic sequence. Okay, so these are the bad boys that I need for an arithmetic sequence. So let me throw them into the corner so that they're nice and handy for an arithmetic sequence. Okay, so it's telling me that the formula that I need is Tn is equal to A plus n minus 1 times D. Now back to my log tables, A is the first term, D is the common difference. Okay, so let's remind ourselves of our sequence. Well, our sequence was 3, 7, 11, 15. Okay, so A, my first term is 3, and D, my common difference is 4. Okay, and N, because I'm creating a formula for Tn, and I'll show you how to use it now in a minute, N stays in. Okay, so you can find any term in this sequence as follows. So A plus n minus 1 times d. So this d that they've written at the end, no idea why that's there and not in front like we would normally place it. Okay, but wouldn't we normally write it as 3 plus 4 times n minus 1? I haven't done anything to get from this line to this line. I've literally just relocated the 4 in front of the brackets because that's how we do most of our algebra. Okay, so you can see now it's 3 plus 4 by n is 4n, 4 by minus 1 is minus 4. Okay, let's tidy up the two numbers. I can't merge the n's and numbers, but I can certainly do 3 minus 4. So Tn is equal to 4n, 3 minus 4 is minus 1. Okay, and that's all there is to coming up with the Tn formula. But you have to first establish your type of sequence. You have to know that the formula is in the log tables. Sub in your A and D and don't get confused with that 4 being at the end. And that's what you do. So for example, what have I just come up with? Well, remember we worked out the 10th pattern and we had to do all of this, okay? Well, once you have this Tn formula, okay, I'd like to know how many is in my 10th pattern. Okay, so let's see, does our formula work? Let's try T10. Okay, what is my 10th term? So you sub in now n for 10. So that's why n stayed n in the formula, because it became this placeholder to sub in whatever term you were trying to find. So for the 10th term, n is 10 minus 1. So that's 40 minus 1, so it's 39, which thankfully is what we got over here. So that's the power of the Tn formula. If I asked you for the 20th term, you have two choices. You can either continue the table up to 20, or you can develop this formula and just sub in the 20. So 4 times 20 minus 1, 4 noughts are naught, for 2s are 8, so 79 tiles. Okay, so that's the power of the Tn formula. So that's what you're coming up for, a formula with a placeholder in it that will give you any term, whatever is the nth term that you're looking for. So remember, Tn is the formula we use when we're finding a formula to give us the nth term. Sn, and we'll use that later in the question, sums up the first n terms. So if I asked for S4, for example, what I'm actually asking you to do is sum up the first 4 terms. 7 and 3 is 10, and 11 is 21, and 15 is 36. So if I did S4 for this sequence, I would get 36. Okay, but we'll come back to that. Okay, so let's continue with the question. Pattern K has 147 matchsticks where K is an element of n. Find the value of K. So now it's telling me how many matchsticks, and it wants to know what pattern number that is. Okay, so this is the formula that tells you how many matchsticks are in a particular term. So we found out that Tn was equal to 4n minus k. So now we want to know, well, what pattern K, so Tk, has 147 matchsticks, okay? So in other words, 4n minus 1, when is that equal to 147? Okay? And in fact, to be properly correct, I should replace the k with n. Okay, so I want to solve this now. When is 4k minus 1 equal to 47? Okay, well, plus 1 to both sides. I'm just solving it like you would any other algebra. So 4k is equal to 148. Divide by the number in front of the letter. So k is equal to 4, 8, 12, 13, 14, 4, 7, 14, 21, 28. So on the 37th pattern, you would have 147 matchsticks. Okay, and it looks right because remember, just we worked out 20 and it was 79. So yeah, 147 is a good bit above that. So again, the power of that Tn formula. So in any patterns question, what you tend to find in a standard question, now there's some that's a little bit oddy, but in a standard question, they'll ask you to develop a formula for Tn, then they'll ask you to work with Sn. Okay, so expect that. Find a formula for Sn, the total number of matchsticks required in the first n pattern. Okay, so let me take this again. On to the next page. Okay, so now it's the Sn formula we need. Okay, so in this one, Sn is equal to n over 2. So this one's a little bit harder to work with. Only because of fractions and there's a little bit more happening. But just like before, A is the first term, D is the common difference. And if it's a formula for Sn you're developing, n stays n. Okay, because we'd like to be able to create a placeholder to sub in n to be able to sub up a number of terms. Okay, so just like before, A was my first term was 3 and my common difference was 4. Okay, that doesn't change. It's still the same sequence that we're working with. So let's put them in. N over 2, 2 times 3 plus n minus 1 times 4. Okay, so n over 2, 2 3s are 6 plus, now again, you can rewrite that 4 at the front if you wish. Okay, I hope that makes sense. I literally just moved it to the front because it's easier to see. 4 by n is 4n, 4 by minus 1 is minus 4. Okay, so I have n over 2. I have 6 minus 4. It doesn't matter whether the number or the 4n goes first. Okay, so that's my Sn formula there. Okay, you can leave it like that, or you can multiply in the n over 2 if you wish. Okay, so I'll just do it in case anybody has it done. So 4n squared over 2 plus 2n over 2. And the 2's will cancel. So you can get Sn equal to 4n squared. Well, actually that 4 and that 2 will also cancel. So I am getting 2n squared plus n. Okay, but okay to leave it like this too, whichever you prefer. Okay, and then part 3, find the total number of complete patterns in the sequence that can be made using 820 matchsticks. Okay, so in this one, they didn't ask you to sum up a number of patterns. They gave you the answer and they asked you, well, what n is that? So very like this one here. So now they've given you the matchsticks, they've given you the answer, and you have to find the n. Okay, and the reason they did this was if you had left your Sn like this, it's a little bit harder to work with. Okay, because they're asking you when is n over 2 4n plus 2 equal to 820. Okay, so at some stage they're forcing you to multiply that in to give you what we had here. Okay, so when you multiply that in, you get such. Okay, and now you can see, and it happens a bit, you have a quadratic, n squared, n, and a number. So bring him over so that you have 2n squared plus 4n. I know where I got my 4n. Sorry, a typo. It should be just plus n. Minus 820 is equal to 0. Okay, minus b formula is probably the easiest thing for there. A is the number in front of n squared, b is the number in front of n, c is the number on its own. So minus b plus or minus, so x equals or n equals, it's officially n in this question rather than x, but the log tables has x. It doesn't matter which one you put down. B squared minus 4ac all over 2a. Okay, So let's try this. So minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so let me put that square root bit into my calculator. Square root of 1 squared minus 4ac. I got 81 for that when I put it in. Over 2 2s are 4. Okay, so let's split it. So my first n value comes from minus 1 plus 81 over 4. And my second value will come from minus 1 minus 81 over 4. We're splitting this bit here to give us the two answers. Now, two answers won't make sense. So I'm expecting to discard one of the answers because it says find the total number of complete patterns. So it kind of makes sense that there's only going to be one sequence. So let's worry about that after we get the two answers. So when I put the first one in, I get 20. And when I go back and put the other one in, I get minus 41 over 2. Okay, so you can't have a minus pattern because that's going, I don't know what it's going, but you can't have a minus pattern. So we're going to discard that one. So your answer is the 20th pattern. So n is equal to 20. Okay, or not the 20th pattern, the sum of the first 20 patterns. So what does this mean? Where did the A20 come out of? Okay, well, if I go back to this, the sum of 3 plus 7 plus 11 plus 15 plus 19, 23, 27, 31, 35, 39, and the next 10 numbers all add up to A20. The sum of the first 20 patterns adds up to A20. Okay, so that was that. You can see it's quite a long question. It's 60 marks, which is quite a lot out of 150. So we're not done yet. Let's keep going. Part D. The table below shows the number of triangles formed by each pattern for the first two patterns. Complete the number of triangles. Okay, I was trying to figure out what was different. Okay, so the number of triangles this time. Complete the table to show the number of triangles formed for patterns 3 to 6. Okay, so 1 triangle, 3 triangles, 1, 2, 3, 4, 5, 5 triangles. And we're just going to add on 2 more. So 7, 9, 11. Okay, that was easy enough. I'm kind of looking to see, did I miss something, but that was okay. Because I always expect the end of a question to be a little bit harder. So that I suppose that's my thought process. But now here could come the kicker. The area of each triangle is 4 root 3 centimeters cubed. Find correct to the nearest centimeter squared the combined total area covered by the first 15 patterns of the sequence. Okay, by the first 15 patterns. Okay, so there's a couple of ways you could tackle this. We could go pattern 1 is 4 root 3, the combined total area. Pattern 2 then, I have 3 triangles, okay? So 4 root 3 multiplied by 3 is 12 root 3. In the third pattern, I have 5 triangles. Okay, so if each one is 4, I'm going to go 5 4s are 20, root 3. Okay, or of course you can put into your calculator 4 root 3 multiplied by 5. Okay, P4, 7 4s, 28 root 3. P5, 36 root 3. P6, 11 4s, 44 root 3. And you can see what I'm doing, okay? P7 is going to be 13 by 4, 52 root 3. Pattern 8 is 15 by 4, 60 root 3, pattern 9, (13, 15, 17, 19, 21, 23, 25, 27, 29. Okay, so all I'm doing for each pattern is multiplying 15 by the 4, okay, and it's that amount of root 3s. That's how surds work. I just multiply the whole numbers by each other. So 15 by 4 is 60. So now 17 by 4 is 68. 19 by 4, 76. Sorry, P11, 21 by 4, 84, P12, is 23 by 4, which is 92 root 3s, P13, 25 by 4 is 100 root 3s, P14, 108 I presume, and P15 is 29 by 4 equals 116 root 3s, okay? And then you add them all up, okay, because it says the combined total area. So if you add 4 and 12 and 20 and 28 and 36 and 44 and 52 and 60 and 68 and 76 and 84 and 92 and 100, 108, 116, you'll have that many root 3s, okay? So that's what I'm doing here. It's 28 plus 36 plus 44 plus 52 plus 60 plus 68 plus 76 plus 84. I'm just keeping an eye on my calculator that I don't run off the screen. Plus 92 plus 100 plus 108 plus 116. Okay, so 900 root 3 centimeters cubed. Okay, so that's the really long way of doing it. And again, if you're a patterns person, you'd see that there was 8 between each of them. So you're just really adding on 8 every time. Okay, you could also develop a formula for SN. Okay, and that would be, I suppose, the more mathsy way of doing it, okay? So under the number of triangles, you would have area of the triangles, and you would have 4 root 3 for number 1. You'd have 12 root 3 for number 2. And then you'd have 20 root 3 here, and so on and so forth. And you develop a formula for SN and so on and so forth. But what I'm trying to show you is that you don't always need the fancy maths. Sometimes just keep your common sense hat on and you will find a way of doing it.
If you are interested in technology or engineering but are not doing higher level maths, why not consider our Level 7 in Electronic and Computer Engineering? This is a 3-year programme that looks at the design and development of embedded electronic systems. These are the medical devices that keeps us healthy, the consumer devices that keeps us entertained, or the controlled systems that keeps us safe on the road. You can then progress on to the Level 8 in electronics and self-driving technologies, and from there to the Masters.
Check out the link below for more information.